Okay, right. In this video, we are going to look at the Euclidean geometry questions from the November 2018 question paper, starting here with question 8. PON is the diameter of the circle, which means then that will be 90 degrees by angle of semicircle. Centered at OTM is a tangent. Now, since that's a tangent, the angle formed the angle between a tangent and a chord is equal to the angle formed on the chord. And I see the 66 there, so this is also going to be 66. TM is a tangent to the circle at M. A point on the circle R is another point on the circle there, such that OR is parallel to MP. So, well, that's going to be co-interior angles, and I see I can use my ratios because it's a triangle with a parallel lines, prop theorem. NR and MN are drawn, NR and MN are drawn. Let M1 be 66. Calculate with reasons the size of each of the following angles. 8.1.1 angle P, I already said that's going to be 66, and that is by tan chord theorem. Angle M2 is going to be 90 degrees. That's because it's an angle in semicircle. N1, that angle there is going to be 90 plus 66 plus 24 gives me 180. 60, 20 is 80, 24 is 90, yes. Okay, so N1 is going to be 24 by sum of angles in a triangle is 180, and then O2, that angle there, it's also going to be 66 because that's a set of parallel lines, so that's corresponding angles. It's also going to be 66 corresponding angles with ROMP parallel, RO parallel to MP, and then N2, that angle there, I see that angle there is an angle at the circumference formed on MR, so I'm also looking if there's maybe any other angles formed at the circumference, which I don't see, or maybe an angle at the center, which I also don't see here. So something else I might be looking at is I have N1 is 24, is to look at this angle there, and this angle there you see comes from PR, and there is an angle at the center, which that one is not very difficult to get. O1, I'm first going to state O1 because O2 is 66. This angle here, angles on a straight line, is going to be 180 minus 66 is 114. Is that correct? Yes. O1 is 114 angles on a straight line. And then the angle at the center, 114, is going to be double the angle at the circumference. So N1 and 2 together is going then to be 57 degrees angle at center equals twice the angle at the circumference. And then N1 I have as 24, so 24 and what gives me 57 is 33. 33 degrees. N2 is 33 degrees. Well, and there we go. Okay, so that is question 8.1. Let's move to question 8.2. It says here, in the diagram AGH is drawn. F and C are points. F and C are points on AG and AH respectively, such that AF is 20 units, FG is 15 units, CH is 21 units. Okay. I don't have parallel lines here. I immediately think of the prop theorem, but I mean, this is not parallel yet. Maybe I can show it. D is a point on FC such that ABCD is a rectangle. So if that's a rectangle, all for those ABCD, no, rectangle, not a square. Those two lines are equal and those two lines are equal. And that's a 90 degree, so I can maybe use that. And also for rectangle, you should know that the diagonals bisect one another, although they are not equal, are they? For a rectangle? Yes. This side and this diagonal and this diagonal will be equal and they bisect one another. So all four those lengths will be equal, which helps me a bit out with the ratios there at least. So the fact that ABCD is a rectangle is very useful. There's a lot of information in that. With AB also parallel to GH, AB parallel to GH, the diagonals of ABCD intersect at M, a point on AH. So at M there, a point on AH. Explain why FC is parallel to GH, which is something that I want to use. I want to try and show why FC is parallel to FH. So this is parallel to that. GH is parallel to AB, but FC is also going to be parallel to AB because this is a rectangle and the opposite sides of a rectangle are parallel. So both this line and that line parallel to AB. So I can write that. Let me somewhere write my here on this. AB is parallel to GH. That was given. And AB is parallel to FC because they are sides of a rectangle. Those two. So since both these are equal, parallel to AB, then they will be parallel to one another. They are both parallel to AB. So then FC will be parallel to GH. They are parallel to AB. Calculate with reasons the length of DM. This length here. Nope. DM. Where is DM? There. DM. So, I mean, DM is also going to be the length of AM and MC. And if those are parallel, I can very easily get the length of AC because AF prop theorem, AF to FG is going to be the same ratio as AC to CH, AC to CH by the proportion theorem. Since I have these parallel lines FC and GH in the previous question, AF is given as 20, FG is given as 15, IC is what I want to calculate here, and CH is 21. And then well, this can simplify to 4 over 3 divided by 5 divided by 5, which is just going to make my life a lot easier if it's smaller numbers. So 21 times 4 is 84 is equal to 3AC divided by 3 divided by 3. That's 26 is AC. I'm just going to double check myself quickly. That 84 divided by 3 is 28. Oh, you see, good thing I checked. Okay, so AC is 28. AC is 28, and since AC is 28, I'm just going to continue there quickly. So since AM is equal to MC is equal to DM for that matter, because there are my reason, oh, it's so squashed in here now, is going to be diagonals of rectangle, and IMMC is IC, which is 28. IMMC is each going to be 14, half of 28, so that also makes DM 14 for that matter. Okay, that's question 8 of the November paper 2018 paper. We're moving to question 9. Question 9.1 is just a proof, but I will quickly run you through it. It's the proof that opposite angles of a cyclic quad are supplementary. That theorem in the diagram JKLM is a cyclic quad in a circle that has a center O. Prove the theorem that states that J plus L is 180. Now, if you want to prove J and L 180, you connect the other two sides to the center with a ruler. I don't have my ruler here with me, but when you do this in a test or exam, please do it with a ruler, and please also draw this not on your question paper but in your answer book, so that the person marking can see the construction that you made. And I'm just going to number this 1 and 2. So O1 is double J. O1 is double the value of J by angle at center equals twice the angle at circumference, and O2 is double L. Same reason. Rather write out the reason than just write same reason. Write out the reason. Please don't be lazy. If I can write it out, you can write it out as well. Right. Okay. And then O1 and 2 together, there is a full revolution 360. Is 360 because it's angles around a point. So O1 is 2J plus O2 is 2L. I just substitute equal angles there is 360, meaning if I divide by 2 throughout, that J plus L is 180, and that's what I wanted to show in this question. Alright, then question 9.2, this looks insane. What do you do when a question looks insane? Don't just leave it and continue. Look at it. Maybe it's not that hard. In the diagram, a smaller circle ABT and a bigger circle BDRT are given. BT is a common chord, so BT there lies in the circle, and BT lies in the circle common chord. Straight lines STD and ATR, STD and ATR are drawn. Chords AS and DR are produced. AS are produced, DR produced to meet at C, a point outside the two circles. BS and BD are drawn. BS and BD. A is equal to X, that angle there, and R1 is equal to Y, that angle there. 9 giving a reason another angle equal to X. Now in this circle, if that's X on the same chord in the same segment, B1 is also equal to X angles in same segment. Y is an exterior angle of this cyclic quad RTBD, so the opposite angle B2 will be equal to Y. That's because of exterior angle of cyclic quad. Prove that SCDB is a cyclic quad. SCDB is a cyclic quad. Now, to prove a cyclic quad, you can do one of three things. You prove that the exterior angle is equal to the opposite interior angle, which I can already see I can do here because this exterior angle is equal to S1 is equal to T2 by angles in the same segment, and then T2 is equal to D1 and 2 because that is an actual cyclic quad. So there, and then S1 is equal to D1 and 2. So the exterior angle of this quad there is equal to the opposite interior, making it a cyclic quad. But the other two reasons that you can also look for and maybe use is that the opposite angles must be supplementary. So if you can show that to be true, or if you can show angles in the same segment equal, which I don't think you're going to be able to do here. I'm just going to write this on paper 9.2.2. I have proof that SCDB, so S1 is equal to T2. S1 is equal to T2. Those are angles in the same segment, and then T2 is equal to T2 in this cyclic quad is equal to D1 and 2 together, because it's an exterior angle of cyclic quad. And since there's quite a few cyclic quads involved in this question, it's the exterior angle of cyclic quad T or DB. I'm just going to be T or DB, be very specific. So then S1 is equal to D1 and 2, and that is an exterior angle of the opposite interior of this. So that makes SCDB. SCDB is a cyclic quad, and I used the converse of exterior angle of cyclic quad in this question. Okay, then 9.2.3, if it is further given that D2 is 30, so this angle there is 30, and AST there, AST is 100, so that angle there is 100. Prove that SD is not a diameter of the circle BDS. I want to prove that this is not a diameter. So I basically want to show that's not 90 degrees. Okay. So that's 30 degrees. This is 100. And since this is the exterior angle of this triangle there, that's 100. This is 30. That's going to be 70. Making that there 110, the B1 and 2. So that's not a 90. So if that's then 110, SD is definitely not a diameter. So that's what I'm going to do. I'm going to say that angle 9.2.3, angle C is 70 by exterior angle of triangle, and name SCD because there's so many triangles and things going on this sketch. The exterior angle of this triangle SCD, that's 100, this is 30, that's 70. So C is 70, that makes B1 and 2 going to be 110 because opposite angles of cyclic quad or supplementary. And since many cyclic quads here, I'm specifically talking about the SCDB, which I've proved the cyclic quad in the previous question. So the opposite angles of cyclic quad SCDB or 180, that makes that 110, which means B1 and 2 is not 90 because it's 110, and that means that SD is not a diameter of circle BDS. BDS. Okay, because the angle in the semicircle is not 90, so that's not a semicircle, so it's not a diameter. Okay, that's question 9.2.3. We'll close off with question 10 from this question paper. Right, this is not a very long video so far. I hope this does not take us hours now, but let's quickly see. Question 10. In the diagram triangle, or in the diagram ABCD is a cyclic quad. There, okay, we've got a cyclic quad. Also, then the exterior angle of a cyclic quad is equal to the opposite interior, which is x. So I'm going to just mark myself there an x to remind myself there. That's the cyclic quad to the exterior angle, x cyclic quad, such that AC is perpendicular. AC is perpendicular to BC. It's shown there. DC is equal to CB, and since I have two equal chords, the angles on them is also going to be equal. It's like that angles in the same segment. If I split the segments into two different chords that's equal, they will still be equal. It's just a corollary or an extension of angles in the same segment. If the two chords are separate but it's equal, and it's also going to extend equal angles at the circumference. AD is produced to M such that AM is perpendicular to MC. It's not given that this is a tangent anywhere in the sketch, so don't just assume tangents. But oh, you see here they want you to prove that MC is a tangent, so don't just assume. Let B be equal to X, so B is equal to X, that's equal to X. Ultimately, that's 90 minus x C2, and that's also 90 minus x, right? Because 90 minus 180 minus 90 minus x is going to be 90 minus x, and 180 minus 90 minus x is going to be 90 minus x. You see the 90 and the x and that angle, the 90 and the x and that angle makes those two angles equal. So the first thing I want to do, prove that MC is a tangent. I want to show that the angle between a tangent and a chord, the angle between a tangent and a chord is equal to the angle formed on that chord. I can show this one is equal to that one, and then that one is equal to that one. So angle C2, question 10.1.1, angle C2 is equal to, oh, I must actually first state that D2 is x because that was not given. So let's just start there. Angle D2 is equal to x because of exterior angle of cyclic quad. And then angle C2 is going to be 180 minus 90 minus x. 180 minus 90 minus x by sum of angles in a triangle, and then that is 180 minus 90 is 90 minus x. So C2 is 90 minus x, and okay, then A2 is equal to 180 minus 90 minus x. A2 is 180 minus 90 minus x, also by sum of angles in a triangle, sum of angles in the triangle, then A2 is also 90 minus x. So that makes A2 equal to C2, right? And A1 is equal to A2 because they are angles equal chords, equal angles is that reason, I believe. Equal chords, equal angles, equal angles. It's like angles in the same segment, but equal chords, equal angles. You also have, if you have two equal circles, equal chords, equal angles, you can also extend. Okay, so then you see both these, that makes A1 equal to C2. So if A1 is equal to C2, that means that MC is a tangent because of converse of tan chord theorem. Tan chord theorem. Okay, the tan chord theorem says if this is a tangent, the angle between the tangent and a chord, that angle will be equal to the angle formed on that chord in the alternate segment. So on this side, this angle, in the other segment on the circumference, those two will be equal. But now what I've done here is I've shown that those two are equal, hence that is a tangent. So I'm using it backwards, that's why I'm saying the converse of. So MC is a tangent. Prove that triangle ACB, this one here, is similar to triangle CMD, this one here. So that's not a difficult proof. I have 90, x, and angle, which I've already proven equal. I must just write that down literally. So this is not going to be a challenge at all. I can just say in triangle ACB, let's say angle ACB is equal to CMD DMC. They were both 90 given to me, right? So ACB, that one there, is equal to DMC, that one there. They are both equal to 90 given to me. I don't even need to state a reason. Then I'm working with ACB, this one first. So then the angle B is equal to the angle D2. D2, they are both equal to x, and I've already said in question 10.1.1 that D2 is x. The B was given as x. I already said that D2 is x, so I don't need to give reasons again, but it's the exterior angle of a cyclic quad. And then I'm working in this triangle first. I said the angle C, the angle B, so I'm still looking for angle I2 is equal to, and here I've set the angle M, I've set the angle D2, so I'm still looking for angle C2. So I2 must be equal to C2, but I already proved that also in 10.1.1. So I can just say from 10.1.1, or you can give the reason again, but really it's not necessary. Or if you've already proved two angles equal, you can just give a reason, third angle of the triangles. That will also be valid. So triangle CBA, let's call it ABC, rather, triangle ABC. If I list here ABC, I must list CDM on that side. Is similar to triangle CDM by angle, angle, angle. And then question 10.2.1. I'm just going to quickly rewrite those two triangles here. I have ABC, CDM. I have from the previous question triangle ABC similar to triangle CDM in that order. It's important that I've proven, because now in the next question they say hence or otherwise prove that CM squared over DC squared is AM over AB. CM DC AM IB. Sure. IM. I'm gonna just start by this. So question 10.2.1, from the similarity there I have AB over CD is equal to BC over DM. BC over DM is equal to IC over CM. IC over CM. Here is something that we can do, starting off with where we started, IB over D over CD is equal to, oh, rather using these ones that I said now, rather using them, is AB over CD is equal to BC over DM, rather using those ones. And then remember, BC and DC is the same thing, right? So I can replace the BC with a DC. So AB over CD or DC, CD, AB over CD, BC is also CD, is CD over DM, and then cross multiplying here. So CD times CD is CD squared, and AB times DM is AB times DM. Now that gives me the CD or DC squared. So I'm also trying to get CM squared, now something else. CM squared, I want to, well, my inkling is to use Pythagoras. CM squared is AC squared minus AM squared. But I want to try and stay away from a plus or minus because that creates a bit of a challenge for me here, right? So I'm rather going to try and do MC squared in this triangle and that triangle. So I also want to try and show that these two triangles are maybe similar. So let's do that. I have in this triangle DCM, and the big one AMC, triangle AMC. I have that angle M is equal to angle M, it's 90 and it's common. 90 common. Then angle C2 is equal to angle A1. DCM is the small triangle on the left hand side, so C2 is equal to A1 in the big triangle. I've shown that in 10.1.1, 10.1.1 or 2, I'm not sure now. And then C2, D2 is the last angle there. D2, which is X, will be equal to C1 and 2 by default because it's the third angles of the triangle. Then I have that triangle MCD. MCD is similar to triangle MAC. MAC. And from this, I can write down that MC over MD is equal to, MC over MA, sorry. MC over MA is CD over AC. AC is MD over MC, MD over MC. And from this, I'm trying to get CM squared. So CM or MC, same thing. So I'm going to work with this one and this one. So I see that CM times CM, CM squared is equal to MA times MD, or AM times DM is probably better if you write them alphabetical. So I'm trying to get here CM squared over CD squared. So CM squared is AM times DM over, and that's AB times DB times DB. DM I want to show that this is actually equal to AM times AB. You see CM squared times CD squared is AM over AB. So I want the DM and the DB to cancel somehow. DM and the DB to cancel. Have I now done this wrong? MC, MA times MD. AB times CD, AB times DM. That's not DM. DB, DM. CD times CD, CD squared, IB times DM. Sorry, made a mistake there. Oh, thank goodness. So this CD is IB times DM. Sorry. Yeah, that looks better. And then that will cancel, leaving me the desired result there. Okay, and then question 10.2.2 says show that AM over AB, which is that, is equal to sine squared x. Right, show that. AM over AB. Okay, so is sine x. Now I'm probably going to work with CM over DC. Let's quickly see CM over DC. Oh, great. So there's a x, sine of that x opposite over adjacent. CM over DC, you see that. So 10.2.2, sine x is equal to CM over DC. Sine of x is opposite over hypotenuse CM over DC. And if I square this, CM squared over DC squared, sine squared is CM over DC squared, which is that. And then I've shown that this is equal to AM over AB. So AM over AB equals sine squared x. Okay, that was not difficult. And that is the questions from the November 2018 question paper on Euclidean geometry. I hope this really helped you. Good luck and keep working hard.